Hi everyone. In this video, I'm going to show you the two mode of reactivity for a sugar, right? And just like in all the other aspect of organic chemistry, sugar will also only have two mode of reactivity, which is a nucleophile and an electrophile, right? And that's just been the theme throughout organic chemistry, where you had a nucleophile and an electrophile coming together, right? So sugar is no different, right? So there will be two distinct mode of reactivity. And the way you'll be able to tell which pathway you're going through, if it's a nucleophile or electrophile, is one, by looking at the reagent, okay? So typically, if you're given an electrophile and a base, right? If you're given an electrophile and a base, that means you're looking for the nucleophile. That means in that case, the sugar will act as a nucleophile. Versus where if you're given an acid and a nucleophile, right? So if you're given a nucleophile, that means the sugar will act as the electrophile, okay? So what part of sugar is the electrophile and what part of sugar is the nucleophile, right? So let's look at it. So here we have the sugar. This one is alpha D allopyranose, right? For those of you that are still a little confused about the name, just think about, right? Alpha means this anomeric position. If it's down, it's alpha. D means this CH2OH. If it's up, that means it's D. Okay, so on. And since on the first reaction pathway, you're reacting with excess acidic anhydride and pyridine. So for those of you that don't know what acidic anhydride looks like, it looks like this thing right here, right? So the way you could think about it is that this could be the electrophile and that whole thing leaves. So that's your leaving group. So this is the leaving group. That's the electrophile, okay? So if you're given an electrophile, that means the sugar will be the nucleophile, but what part of sugar is the nucleophile? So all these free hydroxyl groups you see here, you guys know that alcohols are generally nucleophilic, right? And then sugar has many of them, right? As you can see on this sugar, there are 5 alcohols, right? And if you're given an excess, right, that means there's no abundance of the electrophile. That means all 5 of them will react to give you whatever the product is. So let's look at how that works, okay? So if you have your electrophile, let's draw it out, right? Let's just draw with this alcohol right here, but you could do it with any of them, right? So the first step is gonna attack the electrophile and push the arrow up, right? And then let me show you the mechanism. I'll just draw that OH out explicitly, and then the rest of them I'll just put sugar, right? So then what happens is we attached it there. It's plus charge, that's minus charge, right? You have a methyl group here, and you have this thing right there, okay? So the next step is you have a base, right? You're giving a pyridine, right? So what the pyridine does is it will grab the proton, because we don't need the proton there, and that will give you okay, something that looks like this, right? So now what will happen is this electron will come down, right? It could either kick out this bond or that bond, but if it kicks on the bond on the left, you're back to your starting material, so that doesn't do us any good. So what we're gonna do is kick the bond out to the right, right? So if I kick out the bond out to the right, what you get is something that looks like this. So this is what we call isolating, right? So we isolated the sugar so instead of free hydroxyls, now all the OHs on the sugar will be protected. So I'll just erase this. I can draw the product. So you have the pyranose. Okay. So I'll just draw it out. So you have, now it looks like this, right? And all the OHs look like that, okay? So all the OHs will look like that. So you could either draw that, or you could also write OAC. OAC, OAC, okay? So that's one way of protecting sugar, right? By isolating it. The second one is almost the same thing, except your electrophile is different, right? In this case, much simpler electrophile is an alkylate electrophile. So we'll just do an SN2, right? So instead of having OAC in your sugar, it will be, so I'll just draw out one of them. So it'll be O, 1, 2, 3, 4, 1, 2, 3, 4 carbon, okay? So this is an ether, right? So this is a sugar that is ether protected, okay? All right. Now, this condition right here, it's different, right? So instead of giving you an electrophile and base, we're giving you nucleophile and acid, right? So if we're giving nucleophile and acid, your sugar will be the electrophile. But as we already discussed, the alcohol of the sugar, right, they're nucleophile. They can't really be converted to electrophile, right? But there's a specific position, very special position that could be used as an electrophile. That is the anomeric carbon, okay? So how does this process work? So you're given an acid, right? So if you're given an acid, what's going to happen is this alcohol right here on the anomeric carbon will grab the acid, okay? And that will make this. And you guys know that if you protonate an alcohol, right? Protonate alcohol, it becomes a good leaving group. Now, you could protonate all the other alcohols, right? There's nothing stopping you, right? But once you do that, we can't really carry forward what we want to do, right? So that's why, yeah, sure, the other proton gets protonated, but this one is the one that matters, okay? So then what happens is because it becomes a good leaving group, we'll kick out the water and it become this thing, what we call oxonium, right? All the other substrate is still there. I'll just don't draw it. You could draw it yourself for practice. It becomes this thing called oxocarbenium. Positively charged, that's what it's called, an ium. And if you notice, right, this looks a lot like an aldehyde. In fact, that's what you kind of call sugar an aldehyde, right? C-double-O, an H right there, right? And in fact, it's even better than an aldehyde, right? Think of an aldehyde that is positively charged, that is locked in a ring, right? That must be super electrophilic. So because it's so electrophilic, right, and you're given an alcohol, given a nucleophile, just this, will come and open it. Not open it, but will attack. And then after the proton transfer, you get, okay? So that's the only way of modifying the anomeric position from a free OH to some sort of ether, okay? And this reaction is reversible where you could go back to the oxocarbenium and the water could come back and attack, okay? So remember, sugars acting as an electrophile will only do chemistry on the anomeric position. Sugar acting as a nucleophile will do chemistry in all the other positions.